Hello everyone, welcome to our Open Power Academia and Research webinar. I'm glad to see you all here, and I've got high confidence for what we can achieve while we are here as part of this Open Power Academia and Research collaborations. Today we have Dr. Samir Shande, who has been serving as the Director of Performance Research at University of Oregon, and also we have Andrew Zhang from IBM, who is our data scientist, going to be sharing some experiences with their tools, as well as the Power9 the performance capabilities. Today's sessions will be recorded and shared, and I'd like to invite Dr. Samir to go ahead and start the session.
Thank you, Ganesan. Thank you for inviting me for this webinar. My talk here today involves performance evaluation tools, and I'll specifically be talking about the TAU performance system and the extreme scale scientific software stack, or E4S. So there are two main challenges that I would like to cover today. The first is that with growing hardware complexity, it's getting harder and harder to accurately measure and tune our applications that are based around HPC and AI and machine learning workloads, and to identify where exactly the time is being spent when there are multiple levels of transformation in our application frameworks. And secondly, as our software gets more and more complex, it's getting very hard to install the tools, libraries correctly and in a well-validated manner in an integrated and interoperable software stack. So to address this, we are presenting two tools to improve your productivity. The first is the TAU performance system that aims to deliver a scalable, portable, and performance evaluation toolkit for our workloads. And the second is the extreme scale scientific software stack, or E4S as we like to call it, which delivers a modular, interoperable, and deployable software stack that has many of the commonly used HPC numerical libraries, runtime systems, compilers, and other tools. And it delivers expanded and vertically integrated software stacks so that you can achieve the full potential of your hardware platform. Our goal is to lower this barrier to using software technology products from the Exascale Computing Project and to enable uniform APIs where possible. The TAU performance system has three main components to it. There's the instrumentation component, where you add hooks to measure your application performance. And you can automatically add hooks for a number of languages, including C, C++, Fortran, Python, and even Java. And we also have source analysis tools like PDT. You can intercept the library calls. You can even add hooks at the linking stage or at the executable stage. And all of these hooks essentially call a measurement API, and you can enable profiling or tracing, which then generates performance data in the form of profiles or summary statistics, or traces, which are event logs that are time-stamped. And you can view these profiles using Paraprof, a profile browser that comes with TAU, or you can use third-party tools such as JumpShot or Vampire to view the traces. So TAU supports instrumentation of a large number of languages, as shown, as well as many runtime systems. And so if your application is using, say, MPI or OpenSHMEM or pthread or OpenMP or CUDA or OpenACC for that matter, you can automatically instrument your code and intercept the calls to the runtime system, and then measure exactly how much time was spent in that call. And you can generate profiles and traces, and then even upload the data to a TAUDB database. So you're probably wondering, what can TAU show me? Well, it can show you how much time was spent in your application at the routine level, at the outer loop level, or even within the loops. You can see the statement level contribution. You can see the time spent in individual OpenMP loops. in kernels executing on GPUs, you can even see the data transfer that takes place between the host and the GPU. In OpenACC, you can even pinpoint a variable name and say, so many bytes were transferred for that particular variable going from the host to the GPU. We can also look at instructions executed in these codes. Instead of wall clock time, you could see hardware performance counters from PAPI or Liquid. These are libraries that can expose the lower level processor level counters that show floating point instructions, data cache misses, hits, branches, vectorization. And you can correlate this information back to the loop level or to the function. You can see the memory usage of your code, where it's allocated, deallocated, leaks, even the memory footprint. What is the total amount of memory using stack, heap, data, text, BSS, the full memory footprint, and what is the max usage across the execution, the high water mark. You can see the energy usage, IO, and even how the application scales. So the first part that's common to all the tools, performance evaluation tools, is the instrumentation phase, where you add hooks to the code that then perform measurements. You can add these hooks using a preprocessor where source code is instrumented, and a copy of the instrumented source code includes the start and stop calls for the timers. This can be simplified using compiler scripts in TAU. So you can, instead of using, say, MPI CC, you would just say TAU cc.sh or TAU f90.sh for Fortran. You can also have a filter file that can reduce the runtime overhead and narrow the focus of your instrumentation. You can also insert hooks using the compiler itself, where a special flag helps in adding hooks at the routine level. Or you can use runtime preloading. Now, this is really interesting because you don't need to change your application binary in any way. Instead of launching your MPI application as MPI run app, you could just say MPI run TAU exec with some parameters and then app. So you can just insert this one launcher, whether it is an MPI or a non-MPI job. You can use this to identify the time spent in your application. As I mentioned before, profiling will show you the summary statistics. So you'll see how much time is spent total in each routine, whereas tracing will show you along a timeline what each MPI rank or thread of execution was doing, and the messages between ranks. So you can generate the data, performance data, using probes where you have explicit start and stop calls, or indirect methods can be used, such as sampling, where you don't need to change anything in your binary, but a periodic interrupt interrupts the program. So using TAU exec, you can preload a wrapper interposition library that intercepts the runtime system, and then it can call the original library, such as MPI, OpenMP, POSIX.io. You can even see memory allocation and deallocation and create wrapper libraries for external packages. So you can, once you enable TAU exec, you can then enable other options of TAU, such as generate a communication matrix, generate OTF2 traces, or event-based sampling. And this is how you typically use TAU, where you can load a module. This is often how HPC systems install TAU, where they have a specific module for TAU. And then you can just say an uninstrumented application is instrumented at the MPI level using TAU exec-event-based sampling, or EBS. If you have an OpenMP application with MPI, you can just enable the OMPT support level and enable the tags that define the configuration of TAU. Here I'm saying, please use the Clang compiler with OMPT version 5, which is a configuration that is generated when you install TAU, and then enable the OMPT events, or a pthread configuration. Or if you have a Python application, you can just launch, instead of with TAU exec, you can say TAU Python. And the usage is pretty similar. You can enable CUDA profiling with the CUDA profiling tools interface, or CUPT. And if it's without MPI, you must use the serial flag. And then you can just generate the profiles, view them through pprof or paraprof or GUI tool. You can generate trace files by enabling the tracing flags and then automatically launch the Vampire tool after running your program with TAU exec, and then it will be able to show you the traces without requiring any merge or conversion operations that are typically required if you use, say, Chrome browser or jump shot tool. So when you launch Paraprof, this is what you see. You see every MPI rank, and the colors are representing the functions or code regions. And then if you just tag the bars in their own space, you can see one particular function all in its own space. And you can look at the thread statistics window. You can also look at the context window in TAU. And if you use TAU with TAU Python, like this with event-based sampling and kubectl, then you will be able to see the individual kernels that execute on the GPUs and the time spent in those kernels, how many times they're called, the memory transfer, host to device and device to host. Or you can look at the thread statistics table that shows you for a given Python program. Here is the thread statistics table, and it shows you the names of the kernels as they are being launched from the host side. You can see the Python and C interfaces and see where the boundary is between the Python code and C code. Here you can click on these columns and sort them by different ways. And you are seeing over here, the application total time is like 9.3 seconds. These are the MPI functions that were called, and 9.1 seconds were spent exclusively in the application outside of any other MPI calls. And with sampling, it can explain 9.0 out of the 9.1 seconds because you're taking samples periodically, and you can measure exactly which functions were called. Like in this particular case, you're looking at the NAS parallel benchmark application, and you can see that these are the functions, and you can expand them to see exact samples and where they take place like this. And you can expand this 2.89 seconds and say at line number 228 in this solve subs.f, there is a sample which takes so much time, and see the source code. The context event window shows you the actual data transfers between the host and the GPU that you can track. And you can track Python and MPI. All of these are produced on an IBM system. Now you can see over here, this is on Summit, you can see exactly what MPI bcast does. So you can even go inside the vendor library and you can see where it's spending the time. In this case, like out of 12.2 seconds, it's spending 3.2 seconds in a PAMI context lock and pthread spin lock. And you can see where the application is stuck, where it's doing the system calls, and so on. You can even unwind a call stack when you get a particular event by this tau EBS unwind parameter. Here is a application, the TensorFlow application, where you can see the time spent in a eigen GEBP kernel, and you can see exactly how this application, this is a candle application for deep learning from the Exascale Computing Project, and how it spends its time. And you can go down to a specific call site and see exactly what that looks like. Here is the event-based sampling output for a solver in Fortran, where you just have to say tau exec-EBS or enable call sites. So you can see that out of the total time spent in MPI receive, when it was called by the function called exchange1 at line number 68 in exchange1.f, it took about 12.6 seconds, and other instances of MPI receive took less time. So you can partition the time spent in a function based on a specific call site like this. You can look at context events to see the bandwidth obtained in POSIX.io data transfers. So you can see exactly what is the bandwidth per file and the bytes written to each file. IO is getting more and more expensive, and it's important to track the time spent and the data transfers that take place in your application. This is the 3D profile browser that comes with TAU, where you can see all the threads or MPI ranks along one axis. You can see the functions along the other, and the height can be, say, the exclusive time spent in the application. So now this allows you to see the shape of your application. You can see exactly what each rank was doing. Instead of looking at bar charts, you can view the full shape of your application program. Here is a smaller test case where you can see exactly what each rank was doing over here and see the name of the function. This is the shmem barrier all, and you can see at different PEs what is the time taken. And these are the crosshairs for the function and the thread sliders. So you can zoom into a particular point and say at this function, shmem barrier all on MPI on a PE 13, the time spent is 15.6 seconds. You can also see the 3D communication window where TAU shows you the extent of communication between a pair of sender and receiver ranks. And you can even use a different value for height and color value. So you can see exactly how the communication pattern in your application looks like. With event traces, you can see details of all the communication that takes place in your application. In this shmem application, I can see where the communication takes place between PEs and what each PE is doing along a timeline. This is important. You can see what any PE looks like. And jump shot typically shows you boxes within boxes that show you the level of nesting between the parent and the child calls. Here is the Chrome browser, and we all may have Chrome installed on our laptop. And you can just generate traces using TAU for the Chrome browser, and it shows you like a flame graph that shows you the level of nesting that the application calls main, which calls MPI receive, and what the communication looks like between the ranks. And you can just generate these trace files and then load it in your Chrome browser using the Chrome://tracing module. This is the Vampire trace visualizer. It's a commercial trace visualizer. It represents the state of the art in trace visualization. And TAU can generate OTF2 traces when you enable this TAU trace format equals OTF2. And here I'm seeing the timeline display for an application written using the COCOS programming model. COCOS allows you to write the code just once and express parallelism, and then it can generate a different backend for, say, OpenMP, threads, or CUDA, and then you can execute your application and track where the times was spent while keeping a higher level view of your application entities that are represented in the source code. So it provides essentially the X in the MPI plus X, where we look at MPI plus some node level programming model, and helps you create this single source performance portable code where C++ API is used for expressing the parallelism. And then it does this aggressive template metaprogramming to translate that into backends such as OpenMP, pthreads. But we can measure the application's performance and map it back using the COCOS profiling interface, all without changing anything in the application code. So here is an example of a COCOS code where I'm enabling the push region and specifying a update halo, and then this is popped here. And you can look at the COCOS parallel for, where a lambda function is describing the computation. And then here is a kind of a name, a descriptive name, which says this code region is for halo update pack, and this is for halo update self or unpack operations. And you can write this code just once, and then COCOS will generate the backend data. And then you can see phases within this update halo and see what happened for the parallel for COM MPI. And you can see the names of those kernels that were specified by the user, and also look at the OpenMP data at the same time. So you can have parallelism at both the levels exposed by TAU's instrumentation. And here I'm seeing for a given phase like update halo, the time spent in MPI send, as opposed to the time spent in MPI send for the entire application. I'm also able to see the OpenMP region instrumentation. So I can see at once on the IBM AC922 with NVIDIA GPUs, where the time was spent in a particular COM update halo, and then see the Cocos API calls. You can see the samples that show you what's happening in the rest of the code. And then you can see the instrumented parallel for regions, as well as you can look at the CUDA calls. So you can see all the information in the application using the CUDA APIs. You can look at the pthread layer instrumentation. You can look at the slice through the entire layers of your runtime system with TAU with no changes to your binary. And you can see the CUDA events over here. There are many runtimes that TAU supports. In case you're wondering, it supports MPI, pthread, OpenMP, OpenACC, OpenCL as well. We can use CUDA. We have support for ROCm, Cocos, Python, and you can mix and match these runtimes so that you can, for example, if you had a TensorFlow application or a PyTorch application, you could use Python with CUDA, or you could you have Horoward application with MPI, and then get instrumentation at multiple levels, again, without any modifications to your application. We just launch it with TAU exec with the special flags for either kubectl, OpenCL, or OpenMP tools interface to OMPT, specifying the OMPT configuration, or enable event-based sampling with either wall clock time or hardware performance counters at the resolution of file, function, or statement or line level. So with this information about TAU, I would like to move on to the extreme scale scientific software stack, which will help you get TAU installed very easily in your environment. So E4S is a community effort to provide open source software packages and reduce the barriers that we face in installing applications on HPC platforms. It provides both from source builds as well as containers of a broad collection of HPC software packages. And it contains software packages from a variety of different areas like MPI, where we have MPitch, OpenMPI, we have development tools such as TAU, HPC Toolkit, PAPI, numerical libraries from PETC or Trilinos, data and viz tools like Adios, HDF5, ParaView. And these are bundled in software development kits, and the Exascale Computing Project is working towards a periodic hierarchical release process where the software is released through the E4S site. This is our webpage, e4s.io. And all of these SDKs work together in creating a release. And these are curated releases that are based on the Spack package manager. You can download Spack from this spack.io. And we have binary build caches for bare metal installs as well, which include x86-64 as well as PPC64-LE for IBM systems. And also we have container images on Docker Hub and the E4S website of pre-built binaries. You can just grab this image, and it supports natively the GPUs. So you can access your NVIDIA GPUs through the container image. And we also have a validation test suite. We have a virtual box image if you want to try out different container runtimes. We even have an image on Amazon EC2. So E4S is released twice a year, and we have over 45 full release ECPST products and GPU support. And you can see that there is a image here which supports NVIDIA with CUDA 10.1 for PPC64LE. And you can just pull this image from Docker like this. And if you look inside, you'll see that there are these 46 different ECP software technology products that support NVIDIA GPUs. And here is an example of using Python, where I can just load Python and it supports the Watson ML community edition. So you can just say import TensorFlow or Torch or CV2, Pandas, sklearn, Keras. You can say import Matplotlib, NumPy. So it's a very full-featured Python release, all within a Singularity container. If you say torch.cuda.current device, it will show you which GPU is being used. And here it shows you that there are 4 GPUs available. You can look at TensorFlow test is GPU available to then see the access to the GPUs through Singularity. So you just have one container that has a lot of packages that are pre-built for you to use. You can even use the Docker image directly from our web page, E4S.io. Now let me just talk a little bit about Spack, the core technology used to deliver the software in E4S. Spack is a package manager. People think of it as an apps store for supercomputing. So Spack provides the ability to specify versions of software packages that are interoperable or not. It provides a build layer for a large collection of software tools and libraries and supports maintaining interoperability between these packages. And why do we need this? Well, scientific software is becoming extremely complex, and this makes it very challenging for the users to install various packages. Now, this is a dependency graph of various packages of a package called NALU. It's a generalized, unstructured, massively parallel low mark flow application. And you can see that NALU depends on Trilinos, which depends on Parmedis, which depends on Medis, which depends on CMake, ncurses, a lot of these application dependencies. Here is another application, Deal2, which is a C++ finite element library. And the dependency graph is even more complex. There is one from R minor, and you get the idea. If you have to install each package individually, one by one, by compiling it from the source code, it makes the task of installation very challenging. And even proprietary code, such as this, are using many open source packages shown in blue. And we are building an entire ecosystem of applications. There are over 15 applications with 80 software packages on multiple target architectures with multiple compilers, programming models, and versions of each package. If you were to try and install all of these, there'll be over 1 million combinations where each of them has its own set of dependencies. And many centers devote several FTEs to just building and porting applications. It has become so difficult that individual users find it extremely challenging to install large applications. And they often trade reuse for usability. So we must make it easier to install the software. Now, how do you typically install software on a supercomputer? Well, you download all the 16 tarballs that you need, and then you start building them one after the other. And how do you do that? You do a configure, you do a make, you fight with the compiler, you again configure, you make install, and then after doing all that for all 16 applications, if you get a binary, then you run the application and then it says seg faults, and then you start over all over again. Then you might ask, what about modules? Well, modules just expose an installation that somebody else has done, and they just modify paths like LD library path, path environment variable. And you can only use modules for some package that has already been installed. So Spack is a flexible package manager for HPC. You can easily clone Spack, set up an environment variable, and then you can just install a package like TAU. You can just say Spack install TAU, and it will do that. It provides a spec syntax, so you can describe custom configuration. So you could say just spec install TAU, or say, wait, I want version 2.29 of TAU, which is compiled with GCC compiler with the @ symbol. You can specify the version, and with the percentage symbol, you can specify the compiler and say GCC 7.3.0 should be used to build TAU 229. But enable these options like MPI, Python, pthreads, and even specify information for other packages like, but when you use MPI, get the version which is MVAP2, which is version 2.3, built without wrapper RPath. And then you can specify such details. So if they don't exist, Spack will automatically download this MVAP2 2.3 version, build it with those options, then build TAU with the GCC compiler. This syntax is recursive, and you can see what has been installed by using Spack find like this. Multiple package versions can coexist, and Spack is a very mature technology. Its community is rapidly growing, and you can find out more information about it at spack.io. This is what the Exascale Computing Project is using for building all of its software products. We also have Spack build cache and container build pipelines that are available so that you can just use our binaries, which are hosted from the University of Oregon site over here. And then you can look at the recipes for creating those packages, which are all on GitHub over here. You can look at the build cache and see for different Spack packages. There are now actually there are over 5,000 binaries in the S3 mirror, and there's no need to build this from the source code. You can also get bare bones multi-platform images for different architectures. Here is the PPC64 base images of E4S, and we support Ubuntu, Red Hat, and CentOS 7.6. And we support UBI from Red Hat, the Universal Binary Interface, so that binary image, so that you can have multi-platform reproducible Docker recipes. You can see this UBI 7. We also have a container image for Singularity, and you can see the PPC64LE Singularity image. You can just download this and say Singularity exec --NV. This is for access to the NVIDIA CUDA components, so that you can just run this with the bash, specify a startup bash RC, and then Spack is in your path and you can use it. Here is a build pipeline for creating the binaries in GitLab. And you can see the build pipeline running on Ascent. This is at Oak Ridge National Labs, so that we can have reproducible container builds. And we also have a validation test suite that checks the packages and makes sure that what is installed works well. And you have reproducible container builds, which are then customizable. You can have a recipe that says, please install these packages. And you can cherry pick from our big image just what you need to create your own custom image. And you can try out different container runtimes using our VirtualBox image. So with this, there is still a lot of work to be done. We are looking at a DOE LLVM compiler, where many of the research projects funded by ECP are available in a single recent LLVM release. So you can see the features such as the F18 Fortran compiler, the OpenACC support from CLAC, the Pragma Clang directives for optimization, and the TAU components, all made available in a single LLVM release. We're also looking at how we can deploy this well on facilities at the DOE labs. We are looking at scalable startup with full-featured supercontainers, and also improving the launch of MPI applications so that the MPI in your application binary can be replaced by the MPI in the system. So you can get very good performance using the native network interconnects between the nodes on the systems. So in conclusion, I would like to say that TAU provides a versatile tool to measure performance of HPC and AI machine learning workloads. It's part of the bigger ECP E4S project, which provides a well-integrated stack for HPC and AI applications on IBM PC64LE systems. We also have from source builds that can be assisted by this binary build cache. And we have all these container images with packages that are pre-installed in the E4S.io website. You can download TAU from the University of Oregon. And this is where we are located in Eugene at the Performance Research Lab. And I would like to thank our sponsors from the DOE, Department of Defense, National Science Foundation, NASA, CEA, and our partners at the University of Oregon, the Ohio State University, the people who built the MVAP-H2, ParaTools Inc., the developers of TAU Commander, University of Tennessee, Knoxville, the developers of PAPI, TU Dresden, the developers of Vampire, and Hewlett Supercomputing Center, the developers of tools such as Scorpy. I would like to thank the Exascale Computing Project for sponsoring this research. And I can take some questions now.
Participants, now the time for questions.
Well, let me show you a quick demo and see if you have questions after that. Question and answer. Can we get a PDF of the slides? Yes. And I provided the link and here is the PDF of the slides. Did you get that? Okay. So if you want to see this Singularity container, which is just this file that you can download, then you can just say Singularity exec enable the --NV flag for NVIDIA GPU access and download this one file, and you will have all of these tools within your environment. And here is the Singularity. And you can see the POWER9 GPU. And you can see the GPU over here. Python is a fully featured Python release where you say import TensorFlow, it will just load up. And you can see the 4 GPUs from TensorFlow over here. And Torch, PyTorch, TensorFlow, Keras, any of those packages are available to you. So for example, if you wanted to look at simple neural networks, Keras, and say if you wanted to just run this, there's ankeras.py, and I'm just looking at this application, and it's execution using Keras, and I can just use TAU Python because TAU is in my path. And you can just say and it will use the GPUs. It will run this Python code, and you will be able to just generate profile files without modifying your Python application in any way. You are just launching it to CUDA error out of memory. Oh, some other application is using this. Let me just try. Here is an MPI application. And here is the application being launched without TAU, and this is with TAU. So I'm running this code, and if I want to find out how much time is being spent, then I just run it with TAU exec, and then I'll get the profile files, and I can just say pprof and see exactly where the time was spent in the application. It spent about 3.1 seconds on this MPI rank, and you can see inside the MPI, you can see the names of functions and where the samples were taken, and launch it with paraprof. So with this, you have a single container where you can say Spack find, and then you can see all the packages like TAU installed for you. So you don't need to do much. You can just download one single file and then run it with Singularity. And even for packages that are kind of complex, there is an example of an application called Zoltan, which depends on Trilinos. And if I say compile.sh, I'm just doing a make clean and then installing the application. Now this has many libraries, as you can see, a whole bunch of these libraries that are then available to us. So if I just say run.sh, it loads Trilinos from Spack, and then it can build the application and run it. So here it's running it with, and you can see the profile files as well, and see where the time was being spent for individual IO operations. If you just say Spack load -r Trilinos and do an LDD output on the Zoltan, you'll see all the libraries that are loaded from within the container. And there are 113 different libraries that it loads. So you don't have to install any of those solvers. They are all installed from this location. Using Spack. And you can see all of these solvers on the IBM POWER9 system in your path. So with that, it concludes the demo. Please let me know if I can answer any other questions.
Yeah, Dr. Samir, there are two people raised their hands. Let me open up. Prasanna, hold on, I think Sandeep Agarwal. Okay. Sandeep, go ahead, please.
Yeah, so thanks. It was a wonderful presentation. I've just a question that, like you mentioned, that there are pre-compiled applications, or like even they can be compiled with the desired components.
Yes.
Like for specific to HPC applications, like if they have application-specific performance features, like for example, quilting is there in WRF application. So are these enabled by default, or like the user also has a control to enable it, and then it gets compiled according to your criteria.
So you know, Spack is a very versatile package manager where you can look at a particular recipe. Suppose I have an application that has a recipe. You can look at a particular Spack package and then enable some variants where you can compile the application using those variants. As I was saying, that you can use the wrapper rpath variant for the MVAPitch2 package. You can enable the specific compilation using Spack like that. So the answer is yes, you can create custom compiler flags and ways to compile your application using specific features.
Okay.
Does that answer your question?
Yes, yes, definitely. Thank you.
Thank you, Sandeep. Any more questions from the audience or from the panelists?
Well, hi, Samir. I have a question. This is Argo from UW Platteville. So the question is, I have actually two questions. First of all, do you have this, I mean, can TAU work with the Apache Big Data Software Stack?
Aperture Big Data Software Stack?
I mean, these Hadoop and Spark and all these things.
So we have done work with Spark before, yes.
Okay.
And we do support Python, Java, and other languages. If it's using specific runtimes, we can extend TAU easily to adapt to that. Our focus has been on HPC, but we have looked into PySpark before, and we are able to instrument not only the front-end launcher tasks, but also the compute node tasks in PySpark, where you can get the individual breakdown of how much time is being spent in Python in those specific applications.
Okay, that's good to know, because yeah, I wanted to use this app. And also, I mean, do you have any documentation available somewhere for this TAU?
Yes, you can go to the tau.uoregon.edu webpage, and you'll find the documentation and some videos over there. Here is the link, tau.uoregon.edu.
Okay, sure. And the other question is, so let's say I have a running process. So can I probe TAU somehow in the running process in a server?
So we currently have support for TAU exec, where you can launch a task using TAU exec, but we also have interfaces to GDB, and there is a way to launch TAU exec-GDB on an application binary. And then with GDP, you could attach to the process. It's a little more convoluted. We are looking into ways of simplifying that whole process. So it should make it easier in the future. Does that answer your question?
Yeah, sure. So you have some interface with GDB, right? Okay.
Yes, we do have TAU exec-GDB.
Definitely. Thank you. And it was a really great presentation, Samir.
Oh, thank you.
Yeah, thank you, Agya. One more question from audience. Let me allow again, Sandeep Agarwal to talk.
Hi, Sandeep.
Sandeep, go ahead. Sandeep, are you there?
Okay, it was the same question that I had typed, so it's already answered. Thank you.
Oh, okay. Okay, Sandeep. Okay, any more questions? Okay, I think, we covered a lot now. I'd like to thank Dr. Samir for his wonderful presentation on TAU's features as well as the E4S features. I'm very confident that the E4S Singularity Container and TAU's usage with the AI ML stacks, including PyTorch, TensorFlow, and Keras. And these tools, definitely, will be very useful for developing, new applications on the POWER9 platform. And again, I'd like to thank, Dr. Samir for all the support, which he has been providing for Open Power and Power9 academia and research enablement worldwide. And also, he has been providing the Power9 resources to some good projects, all over the world, for the people whoever make request, whoever made request, he has been, supporting our mission too. Thank you, Samir, for all your support.
Thank you very much. Thank you very much for inviting me today, and thank you. I hope you have a good rest of your day. Thanks. Bye.
Thank you. And our next presenter is going to be from IBM, my colleague, Andrew Zhang. And he's going to be sharing some of his experiences, with IBM Watson machine learning accelerators, Power AI Vision, H2O.ai, the tool, machine learning tool, and then the genomics related, the features, what he has been working on. Andrew, I welcome you to start your session.
Just find the unmute button. Can you see my screen now?
Yes, please go ahead.
Okay, good. All right, thank you, Ganesan. I'm going to start. Okay, so I'm Andrew Zhang with IBM, and I'm a data scientist. This is my agenda today. I will have some introduction about deep learning AI opportunities and challenges, and we'll talk about IBM computer vision platform, Vision Insight. I'll dive a little bit into the architecture side of the AI solutions on Power. I'll do a couple of demos with medical imaging solutions. Finally, I will talk about some IBM data and AI response to COVID-19. So I covered the healthcare, education, life science, and government market. I've been my 4 years with IBM. I spent 2 years on open source analytics, 2 years on data and AI, and I joined the high performance computing team last year. So just set the stage that we all know machine learning, deep learning, and the challenge with machine learning is we need to do a lot of manual feature extraction and engineering. This part of work has been done manually. And the other challenge is we have so many algorithms and models need to learn and train. So this is present a challenge for practitioners and data scientists or AI engineers to put this in use. From deep learning perspective, we know that they will kind of automatically learn the features, but also the challenges sometimes come with this black box and need to further understand what's working under the hood. But the deep learning does provide a performance capabilities when you get a deeper neural network and when you have more data feed into the network. And that is compared to traditional machine learning, the scale is the opportunity is there. We know that nowadays a 22-layer deep neural network is not just deep enough; it just keep getting deeper, and we get more and more millions and even billions parameters need to train. So this is present a challenge for people to use, and a lot of open source initiatives and also commercial products try to address the issue with the platform, and so as IBM. So if you really look at the code for machine learning part of it, and it's just a small portion of it, maybe 5% and maybe 10%, but there's a hidden technical debts in this machine learning or AI system. And as a community, we should try to address this together. And here is, some of the opportunities we can contribute. I want to say the other challenge with machine learning and deep learning is a fast moving space in terms of tools. They all, this is probably a year old, but, in my 4 years time, learning big data and AI, it's just like a constant learning and cannot keep up. It's challenging. So organizations are struggling to capture the value. From data side, we know that most of the organizations are still struggling in solving data silo issue. Most of organizations hadn't built a robust platform to deal with unstructured and particular external data. From the governance side, we know that we need a better data management from security perspective, from metadata perspective, from data lineage perspective. So that many organizations realize the problem, but they have come along to try to scale up to address the issue. We know that in the last 4 or 5 years, we have trained or self-taught many data scientists, but still that we find out there's a lack of experienced data scientists to solve a particular domain or organization problem. If you move around, then you have a lot of times to learn from beginning. From the tools and infrastructure perspective, as I mentioned, that there are many other tools to learn, and on the other side, many tools or platforms are being built. So that's the kind of stage of opportunities for AI, deep learning, but also challenges with AI and deep learning. So IBM had a platform to solve some of the problem. It's called a Visual Insight. It just changed the name. Old name was Power AI Vision. It started with as a platform or on IBM Power system, and now we build this across cloud and the x86. These computer vision tasks, these are the problems we try to solve using this particular platform. Very short, brief listing of the key features. It deals with most videos and also images. It comes with some of the good features to prepare data and with pre-trained the model. I'll give a demo so that I can show you a little more clearly on this. So IBM Visual Insight is just a small part of a big ecosystem of IBM AI and data science platform. And this is one way to look at a new type of Kubernetes and container-based environment. You know that IBM acquired Red Hat. We are leveraging on OpenShift as a container manager to manage the different layers of interface. So on the top layer, you got most of the open source and also IBM services and libraries and the product applications. You can see the Snap ML and Watson machine learning. These are the IBM optimized for on the power and optimized in this architecture platform. We also have a highly scalable, optimized high performance environment built on the GPU, CPU accelerator environment. So these are the few key reasons which you should choose IBM Watson Machine Learning Accelerator. So on the top we try to build a simplified environment and integrate it. You know, OpenShift is a better platform or interface to manage Kubernetes. And lots of people complain it's hard to manage or learn Kubernetes in an enterprise or large environment. It's a good technology and platform, but it's not easy to use. From the CPU and power perspective and GPU perspective, we have a good interconnectivity between power system, CPU, and GPU. Manage through the NVLink for large data models, and we also build also open source platform on top of it, leveraging the cutting edge of the open source advancement. We also optimize this training model for faster for performance and for large number of servers. And, you know, Summit is running on Power and run the same type of platform and technology. Yeah, we also have you know, a platform like this, Open Power community, that we also support each other, develop solutions, and both from hardware level and the software level. And this is the key opportunity for us to collaborate. So with that, I'm going to jump into two demos. Since I'm working in the healthcare and life sciences space, so I'll show you two medical image use cases. And the first one, I'll try to show you the user interface, and then the second one, I'll show you a little bit more, you know, large scale end-to-end machine learning pipeline per se. The very first case we're talking about here is a breast cancer classification use case. You know, this is a leading disease for women and comes with a very high mortality rate. And this particular data set help us to train using IBM Visual Insight to get a high accuracy model, and we can inference it in a fast speed in less than 1 second to get a high confidence score. The patient number actually is not that big, even in this aspect. It's like just 82, but we have about a few thousand images with tumor tissues, about 2,000 benign and 5,000 malignant samples. Each one comes with a different, you know, resolution, pixels and channels and format. And this is sometimes in the medical imaging space, you have to specify this and prepare the data to train a good AI system. This is the interface, but let me see if I can switch my screen. Okay, the interface is built by modern web technology and also container based. And you got the first off, you get in, you will get a place to loading the data. Let me see if I'm on VPN. I need to be on VPN. Okay, that's why. 1 second. Let me close it. I think I'm on VP. Okay, good. So now I have some data sets, because each data set is a collection of images. So it can be hundreds, it can be thousands, it can be millions. So you can import data this way that bring you from your desktop. You can upload the images. But there are other techniques to move the data into this platform. I will share with you a little later. You can clone and rename and reset these data sets, and you can add as many as you want. So for this particular demo, I mean, I have some image classification. I have some object detection. For example, in this, you see some of the labels for annotated data, because without the labeling, you wouldn't be able to run the object detection. But for this particular use case, it's a little bit simpler. We call this classification. And I have the categories here already assigned for this 3,000 images. They belong to different, one of the 8 categories, which is classes, and a few hundred each. We have some capability here to just say, if you choose the image, you can assign the category, can reassign, and then I show you how to label the images. For images, we also have capability to do augmentation, so that you can just create more images, sometimes for different reasons, and you can set this like a multiple copies when you want to. You have some auto label capability, means that if you train a particular model, then you can use that model kind of further label the data together. I have used a gun battle model to label some video files. You can transport and exchange the data, same as the data model, machine learning model. So this is the beginning part of the interface. It's very intuitive. And then you come back. Say if you choose all the images here, so I choose one right now. So if I choose and choose, you choose all, then you click the button to train the model. You can train and retrain. I won't do it now, but once you get the next level, you have different type of choices, because we know this is an image classification. Then you can come here to go for GoogleNet. This is by default. We can enable the core ML, then the model once been trained, then it will be ready to port it to like a mobile device. So GoogleNet, if you know, it's a good balance in terms of accuracy and the performance. It's not a huge number of parameters. You know, that's like you know, less than 100 million. But if it's, you know, some in inception models, it takes like even billions of parameters. So, but also GoogleNet performance is good. So IBM have helped you to choose some of the evaluator and choose some of the best optimized default model to train. But you can do the custom model if you want. This is not object detection, but for the sake of the demo, I'll just show you some of the options here. We have FARSA CNN, Tiny YOLO detection. I know detection 2 is coming out from Facebook. So we try to keep them up. I think the next release, we may just add them. So again, you know, some of these models, say FARSA CNN, will try to get you for like high accuracy, but also fast. But some model actually try to be really accurate, and some model should be really fast. So this is like a tiny YOLO is try to be really fast, because sometimes you need to do a little bit of near real-time type of effort, try to get the training done quickly. Especially, we also have an action detection module. You could also, you know, take a video file and label by, say, certain minutes of, say, people swing the bat, or like play sports in certain behavior, you will just record it, and then use a couple examples and train the rest of the videos, and then detect all the activities in a particular, say, hourly long video. So this is pretty powerful. We've been using this for a couple of clients, both for advertising, sports. I'm working with a client on a POC for government law enforcement. So these are the training options you got. So once they get trained, then you will get a model here. So I deleted some of this, but this will be the one we trained. So you could get the performance metrics, some fancy ones, some basics ones. You can see that we can see the progression of the training part and confusion matrix. We have 8 categories or classes, and we have a procession and record score, things like that. You can export model, and then it's going to be interfaced with maybe other systems through some standard like TensorFlow or something. Let's see what else. So I have trained a model, then the model can be deployed. I have a bunch of model deployed here. I got choose this one. You know that if you get this model and API endpoint, you take that link, you can get that into through the other command line, curl, JavaScript, REST API, or any programming language can use or consume this endpoint. And then, so I can, let's see if I can do something. So I have this one, I just tested a little bit this morning. Let's see if it works or not. It doesn't mean always works as accurate as possible. We got the percentage, the file, I forgot, this one, I think the choose of this is probably this one. But the one they detected is this. Let me try a different one. Because this is a Lambola. Let me see this one works. Yeah, this one is correct. So this is 91%. And we can set threshold. The heat map will tell you exactly where the feature is detected with a Lambola. Because this is probably a more visual way for you to know that what you inference is correct or not. So that is, let me see, that's, yeah, that's breast cancer one. I have another one. The other one is we did with, this is also very classic medical image data set. And I know the other company, both IBM, Microsoft, Google had done both research and also for use case perspective. This actually has been deployed probably in Europe and some other countries. I don't think it's approved in the US as FDA, but it's been a good showcase of opportunities we can use medical image, both from healthcare organization perspective and like hospitals and medical research, but also from clinics. Outside the hospital in the rural area, people can use some kind of a modified medical devices using a trained model, because this model can be deployed, trained in the high performance environment, but deployed in the low or low powered edge devices. So okay, let me. I guess maybe it's a little too small. The background for this data set is It's 35,000 images, costs like maybe 70 gig data files, and they are in the 5 classes or categories, and with 0 as no DR, which is normal, and 3 is severe, and 4 is proliferative DR, means that they are, they can be very close to be blind. And if you look at the class 0 and class 4 over here, I mean, I myself couldn't really differentiate this myself much. And if you are trained medical radiologist or eye doctor or medical professional, sometimes you can get them wrong. And they done statistical research and see, taking 15 doctors and look at this, and they sometimes get the 0 wrong, sometimes get the 4 wrong, but a lot of times they couldn't tell 0, 1, 2, 3. They couldn't tell 1, 2, 3. The other background information is the data source. You see this, they come from many different data sources. Therefore, these images come with, some of this kind of very large black background. And for deep learning to recognize this, sometimes they thought these are part of the feature of class 0, but really, they are really not. So you kind of need to solve the issue like this one and this one come with more, center-based eye images, but this one is not. So so that's one issue, and also about the lighting and the other thing. So the data quality is a problem here. The other challenge with the data is you see we have 35,000 images, but we have 25 in non-DR space. Means this large portion of it is normal, no DR or no eye disease potentially. But there are very small number of categories 3 and 4, and we only have 1,500. So if you just take the data set over there and train a model, and then there can be very much leaning towards likely getting to this side, meaning that you could create a bias with this data. But we try to address these issues, use a combination of IBM Visual Insight and also a few other techniques. And here I'm going to also take you to a presentation, a demo. Okay. Let's see screen. Let me close this. I'm using dual monitor, so. I have a video recorded because this will run a little faster. So let me show you. So what's this, right? When we say you download the data and from somewhere or data source, let me put the volume low. So you download the data, right? And then you somehow have to get into a bigger storage. Because you have many files that need to be high performance and large, and but more important, you need to manage it. So when we take the data come with like 5 parts, and then they have different categories mixed in each part, because you can take a part of one and train a complete model. But I want to train all the 7 data sets together. So you need to actually massage the data in a way to have a structure. So here we are using IBM Spectrum Discover, which is an enterprise grade metadata management system to ingest data, catalog the data, and we can also create a report and the and even getting the report into an Excel file. We'll use this Excel file for later stage of the pipeline, because this is the first step in our AI pipeline, prepare data. Second step is try to generate the data sets. You know that if you're dealing with data this size, you want to train a good model, you probably will do this many times with different combination of data. So we use a Python script, try to pick the data set. Say I pick a category 0 and the category 4 only. I only want to pick 2,500 each. Or you choose all the 5 categories, you try 25,000. So that is your option for different iteration. And we're using this Python code to upload the data into, select the data from storage, then using metadata discover, and then we use Python script to call out that metadata and select a different subset of the training data. So in this case, we're tuning 3,600 for category 0 and the category 3, 4. So now we come to, remember I mentioned we have an issue with imbalanced data, right? So then we try to pick some of the data sets which data with small data set, and augmented this into a larger number of images. With deep learning, it's not like human being. It doesn't recognize upside down just like the same as people can realize. So this gives our platform or machine learning neural network to deal with a different type of features. But from data balance perspective, it is being balanced, and the model can be more balanced and trained. In fact, the training part is the easiest part. It's just like you choose a couple clicks, and you don't need to run all the command line and the code. It doesn't mean it gives you the best model, but it gives you a pretty quick snapshot. Just like all the underneath networks, some come with high speed, some come with high performance. High accuracy, some come with a higher cost, right? So this is a low cost, but a high performance. And this is platform, I think from academia, if you install it, I heard this is already free for people to enable. This is on the Power system. And this is the inferencing part. Inferencing that, I show you breast cancer example, which I took 3 times and take from my desktop and put it into inference box and give you a accuracy rate and classification. But what if you want to do like 10,000s? You have a stream data coming in, right? So this notebook give you a capability to inferencing them in batch mode, and also in interactive mode. If I pause a little bit, see where I can find the pause. Couldn't see the button. So it's like 90-something%. Let's see. So I'm taking roughly just 15 or a dozen images, do it in a small group, because I have the metadata, right? I have a metadata, I can choose any number I want, any one I want. So that is this. That is this what I call the AI and machine learning pipeline, right? It's prepare data, generate data set, doing data augmentation, train a model with pre-trained, Google Net, and it's like I'm on this like a 4 GPU cluster, V100, and then I can choose one click, deploy this in API, and it's pretty good for people just getting space into medical imaging. And there's a lot of public data out there, right? So if you get this platform, you can just learn like a dozen of medical use case. And that's what I do, actually. In fact, I'll show you what I try to scale up to learn this, COVID-19. And once I have data, I grab it, I can do it very quickly. And I can see features. But without this platform, you have to get to a command line, you have to write a TensorFlow, you have to get a GPU. So, I mean, this is already, right? So I think that's pretty cool. Then I guess this is not the end. This is probably the beginning, end of the beginning. So as I mentioned, that the training and advance with AI is take more than just maybe IBM Visual Insight, but it's close, right? Because you see, I have notebook, I have TensorFlow, I have GPU, I have pre-trained model, I have everything under the hood. You just don't see it. You see it, through the IBM Visual Insight. But all the capabilities are already built in, right? You can use open source, you can use pandas, you can use a scikit image, OpenCV, right? So I think, people I could collaborate with you if your organization or university, you have interest to advance research or even learn this particular use case and practice, you can contact us, you can contact me, yeah? So I have researchers talking to me, want to write research papers on top of this because we have a GPU, we have already some practice, we have already had some code, we have good understanding of the use case, and we were also talking to organizations to help them to deploy this in the clinical environment, which is hard, but there's a lot of things can be done. I think there's a way to continue drive the performance, pre-processing for the data, getting better data quality. There are opportunity to do further data augmentation, test it out, iterate it out, try different architecture and neural network and see how that works, right? So from IBM Visual Insight perspective, we have many use cases, large and small, globally in all the countries. And I think with COVID-19, people realize that they need more help. They need more timely help to do things like this. And I'm on this Reddit COVID-19 project, the group. I see so many people are talking about innovative ideas, and it's an opportunity for us to step up, taking advantage of IBM Power and IBM Visual Insight, taking advantage of the data and help for groups, right? So maybe this is about the closing. I have a little bit of section talk about COVID-19, but I can finish this section and then maybe we can open some questions. And then I can spend 5 minutes to talk about COVID-19 and to close it out. So I think that to summarize what I have talked about so far, we have the golden age in AI for data, compute, and neural network. They all give us, we have more data, we have a bigger computer, we have a deeper neural network, that's good. But we're still lacking and we're still adding, we're still advancing. I think for a neural network aspect that we need more supervised pre-trained domain specific models. I think, for if we can really scale up like breast cancer and the DR use case, then we need a more global level collaboration on what is really the best pre-trained and use case specific fine tuning for the neural network for this particular one, right? Then data is an issue. We can use GAN to generate. I use the data augmentation to create more data images, but you can use other techniques like GAN. But neural network had a lot of debates over the last year or two on the limits and the opportunities. And I think at today's, I guess people realize it's highly depends on data and the compute, a lack of knowledge. I think probably at a more general AI system, we should combine that knowledge with the data with neural network to get to achieve a better outcome. So that's neural network, right? And so for data, right, we have ImageNet so that we can train a generic image classification and object detection model. Pretty much like GoogleNet can do most of the classification at all. It's just like how good they are. But if we're dealing with a specified, let's say, COVID-19 line cancer or line like COVID-19, then we need a bigger data, right? And that, where is that data, right? And do we have an ImageNet for medical, right? Or particular therapeutic area? We don't. But that's probably something we should do, right? Because nobody can label all the images by themselves or without being scaled up that usage. The other piece is data sharing. I guess if you know that there's a federated learning opportunities, people are approaching and testing in UK and some startup and Google and most of us also. IBM had a big research in this space. So without sharing data, hopefully we can also scale up the machine learning by overcome the data privacy issues. Last but not the least, but we are in the high performance computing space, right? So it's good to see that we have a ML Perf, this type of initiatives. And the last time I see IBM is leading the medical image in this space to get a standard setup for the benchmark and also get the benchmark on the power system. There's an effort both from ML Perf perspective, try to do the large model, small model, because you can deploy this like in low energy devices with 5G. So this is pretty big, in fact. How to optimize that 10 billion parameter and reduce that into, reduce that model for like a 2 gig into 2 meg, right? So that's something people are working on. So all in all, they're open issues, but I think the future is bright for us to continue on this journey. So speak for IBM, me and my team are working for many client engagement, including we have a workshop for discovery, which is free. There's an email on here called aicoc@us.ibm.com. So you can send the email to them and send an email to Ganeshan and me and or your point of contact in IBM, they will get us here. We also do consulting for architecture, 40 hours. I think that's fee-based. Sometimes it may be free, I don't know. So there's a design sprint and also MVP, which I'm working on 2 of them right now. One for MIT and another for the police department. So that is about my 35 minutes talk. And I can take a couple questions.
Andrew, thanks for your wonderful session. Thank you again. Audience, any questions for Andrew? Yeah, one of the questions from the, the question and answers chat window where they are asking, can we get the PDF of the slides? Yes, we will be sharing.
Yeah. And you can follow me on Twitter or something.
Sure.
And I'll post that there also. Okay.
Sure. We'll be sharing, Priya. Thank you for the question. Any more questions from the audience as well as from the panelists?
You can come along and I will take like 2-3 minutes to, you can think about your question. You can raise your hand. You can send a chat. But this is one more thing I want to mention. This COVID-19, IBM also responds with this they call the 6-pack, genomics, medical AI, diagnosis, right? And molecular fit simulation, biomolecular structure, manufacture quality. We have a variety of tools and application built on top of what I just mentioned before, that the platform called the Watson Machine Learning Accelerator. I mean, IBM Visual Insight is just like one of maybe a dozen of it. So these are the both from open source perspective and also from IBM service and the platform perspective.
Andrew,
yeah.
Andrew, there are two questions from the question and answers window. One is actually where the people can get the image, the medical image data sets.
That's a good question. Actually, I'm going to touch about it. Because with this COVID-19, I actually see more opportunities to get the medical data because we have a pressure, right? Everybody under pressure to just try to fight, yeah. So there's many people doing it. But first thing first, you can go to Kaggle and just search for, say in my case, COVID-19. And actually, I could demo that too, maybe, and give you a taste on how that works. So you get Kaggle. So first thing first, if you go there, the very first button here are about 4 use cases for COVID-19. The first one is use natural language to read the scientific literature, which actually I am building a use case for this. Second one is try to forecast the fatality rate. This is like a model for like a hospital and patient data. This effort is try to address on, publish, upload data, and people can just annotate and label them together for further research. And this one is probably for a company called, I think it's Roche. Yeah, Roche. They were share their data and try to do exploratory analysis to answer research questions. I used to work in pharma. Usually pharma company had a big organization to answer both providers and patients on medicine. And that call center is very important to get the knowledge accurately and quickly. And it requires some special knowledge, but also important, you need a better tool to help them to do that, right? You could search. See, I did a search on this. And you can just use any keywords to search. And not always works best. The other way you do is just use Google. And then use, say, chest as 3. But you use combination of Kaggle and the words, and you see usually they come with actually good result also. So that's a short answer for you to how to find the data. I mean, if you in research, you go for articles and journals. Many of the research articles come with the published data, but the problem with that data, usually the data size are small, little smaller. For that, you know, you want to use that for a big deep learning exercises. Sometimes it's not always there. So as I mentioned, we choose some of the use cases not random. We choose some of these cases because there's an industry benchmark. This type of research and data are validated and being utilized. So that's I mean, that's an add-on to answer your question, where to get data. So because I have done like a couple cases, so when they mentioned about COVID-19, my colleague in Europe, he shared some data set. I myself looking for data set. We're actually learning together. I'm learning from him. He's a super smart guy, and he did a wonderful presentation. It took me just like an hour or something, figure out everything, and I can train a model just like this. I couldn't see clearly, but you could see this way. I get like an 82% accurate. I have probably like, let's see, for COVID-19, I only have 190 images. I mix that image with the regular pneumonia X-ray. So this actually is a good way to mix different data set and try to see if they're good. The good thing about this data nowadays, because they're coming from hospital and research, so a lot of people label them, and so we get many different features, particularly like a sex, sex, age, survival rate. I think there's something called offset. Offset means that when you diagnose this, from the diagnosis or from the symptom until when you get hospitalized. So that offset information will be helpful to identify the stage of the image, how severe this your COVID-19 virus have invaded into your body, right? So actually, I show you one more thing. You can get a sense of what people are doing and how they're doing this. This my colleague shared this video, and I'll just steal his and share with you. Not this one. That is, yeah, it is this one. 1 second. So look at what he's doing, right? He had this one. He's try to figure out what he's doing here. He's taking this taking this image files and dropping into this testing model box. He's getting a different type of confidence score. You know, we got the metadata, right? So with that metadata, he is actually testing one by one and to see how can he train an even robust model from here. Because without spending time on data and measure it, evaluate, you're not going to train a good model. And he's doing this type of manual work to get a deeper insight of how this works. And the good thing with this is he even myself believe that we're going to get more data along the way. The challenge is whether we can get a good quality of that metadata in all the fields, you know. We have some of the fields populated, but not all the fields populated. But generally speaking, we get an age, gender, offset, survival. So you can do some exploration, write a Python visualization and things like that. Yeah, so
okay.
That's about it.
Yeah, thank you, Andrew, for detailed explanation. And We have some more questions on the question and answer chat window.
Okay.
The next one is actually from Gunashekaran M, and he's asking about, for finding growth of a plant, which image processing algorithm will give more accurate results?
Can you repeat the question again? I think I kind of get it, but not completely. Yeah.
For finding growth of a plant, which image processing algorithm will give you more accurate results?
Accurate resource?
Yeah, result, accuracy, more
Result.
accuracy. Yeah.
Right. Finding growth of a plant. I'm not probably not the person know this use case. My understanding is in terms of the result, actually depends on maybe depends on three or four things. Number one is, do you have data? If you have a better, more labeled, annotated data, you probably have to get a better result than a guy who had a supercomputer who's really good on training like a dozen of different images algorithms. You probably beat him, you know? So that's one. Two is depends on how good you are efficient with the tool you use. Because maybe you're good on Python, but you're not so good as a guy then who is doing maybe traditional machine learning or even use R or MATLAB. So it's hard to say you will beat him. It depends on how good you master your tool to develop this algorithm and model. I guess a lot of times it depends on people's preference. I guess I couldn't answer your question just specifically, but I guess if you get into a particular use case, you will talk to more people, and then hopefully you read some blogs, particularly for Kaggle. They have, winners, many of them have been writing some blogs. For the DR case, I have read a few of them. Some of them I couldn't understood, especially in the very beginning. What type of combination of techniques they do. Because if you see, it's not just training the model, right? It's actually preparing data too. If you don't have that data augmentation, you don't have that remove the black background, your model looks like good, but in reality, it's overfitting and is not working, right? So.
Okay, thank you, Andrew. There are, a few more questions, similar to that. Probably, we can take that question offline.
Right.
And let's actually get into the conclusion. Thank you again, Andrew, for your wonderful presentation on all these the use cases which you explained. This is very important, during this, right now at the challenging time. Thank you very much. Again, I would like to thank the presenters, Dr. Samir Shande and also Andrew Zhang for their presentations today. I would like to thank Professor Agia for the great support, and Clarice Edgelin from IBM as part of the panelists too. Also, I'd like to thank the participants for all kindness and efforts to participate in this webinar from Open Power and Power9 Academia team. Looking forward to meet you all on May 8th webinar with the University of Washington. Thank you very much, team. Thank you. Thanks to all.